Welcome everyone to our lecture on the chapter of laws of motion. So today we will be doing the topic of constraint relations. After doing a lot of questions on the idea of pulley-block system and the idea of normal forces, we are finally going to do some more complex questions and discuss what is the idea behind the topic of constraint relations. So, constraint relations in itself means how the motions of two particles on a body being related to each other. Now, these particles can be on a rod, and by that we mean is that if a certain body is moving in that way, in one way, then how the other body would move, and this is basically the question. So let us see what we are going to discuss. So constraint relations consist of a pulley-block system constraint. It also consists of a wedge and a rod constraint, and a single rod and a kept on a wall constraint, a rod kept on a hemisphere constraints. So all these are constraints, and we'll be discussing them one by one. But by far, one of the most common problems which we one of the most common questions which we see while doing constraint relations is the pulley and the block system. So what is special about the pulley and the block system? So uh, first we will be learning something new before learning about constraint. So what we will be learning is instantaneous power. So we'll be defining instantaneous power by a force as the dot product of the force and the velocity. That is the instantaneous power delivered by a force is F dot V. So here it is not important what is power, although you might be knowing what is the definition of power and all that. But for now that is not important. What we are defining is that power is equal to the dot product of the force acting on the body and the velocity of the body. So what we are going to apply is that whenever there is going to be a string and that string is going over the top of the pulley, by that we mean is that the string is in contact with the pulley, it is going on top of it, it is connected to a block, it is connected to another pulley and so on. So whenever the pulley is having some velocity v, then the string has some velocity v. So how that string exerts a force on the pulley. So yeah, what you meant to say is that let's say the pulley has the velocity v. Let's say this is the pulley, and there is a string going on top of it like this. Let's say these are the strings, and tension T is acting on the pulley. So if we want to calculate what is the power delivered by the string on the pulley, so first we'll be calculating the power at 2 points, point number 1 and point number 2. So the points at which the tension is acting, or the points at which the force is acting, are the points which we consider, and we'll be to calculate what, we'll be thinking about what are the velocities of whatever points. So these are the things which are used to calculate the instantaneous power. That is what we meant by saying that the instantaneous power is equal to the dot product of force and velocity. So what idea which we are going to use, now the concept behind doing these problems, now what we are going to use is that when multiple blocks and or pulleys are connected by a light string, For example, like a case like this, and it's not important what the case which we are taking. So let's say you have a pulley and there is one more pulley. That pulley is also connected to some block, and this is the string. So the string which we are drawing, which we have colored the string by the sky blue color. So this is a string which we are thinking about. So the trick which we are going to use, or the idea which we are going to use, is that the power delivered, that is the same thing which we calculate in this equation. The power delivered by this string on all the points or on all the bodies in its contact must add up to 0. That is the total power delivered by the string on all the bodies connected to it should be 0. And by connected we mean that all the bodies which are in contact with it. So the pulley is in contact with the string here. It is in contact with the string here. It is in contact with the string here. It is in contact with the string here. So we can argue that, okay, what are the other contact points? This is the contact point with the block. This is the contact point with the wall, and these are the 6 contact points which we have figured out till now. What about the contact points over the pulley? So the superficial contact points, or when the contact points becomes contiguous, that points we can omit. What we want is that what is the power delivered to the pulley. So to the pulley, the tension acts in this direction and that this direction. The internal tension, it gets cancelled out, we can say, and only these two tensions are usually considered. So this is the idea. So the idea then becomes that sum of all the instantaneous power delivered by the tension to all the points in contact, and then we sum it, must come out to be 0. So that is the idea which is marked in this box. Then one line is given. Additionally, velocities of all the points on a taut string, taut means tight, or a rigid rod, along the rod must be equal. So this is one more point, and we will be discussing this also. So this is also an important point. Okay, so let us apply what we have learned. So let us take this case only, which we just drew. And this is the first case in our problem. So we have a pulley. So pulley we are going to draw by red, and the string which we are going to draw by blue. So these are the strings. We are going to draw the clamp by green and the ceiling by green also. And let us say the blocks are yellow. So we have drawn a diagram in which each thing can be distinct, can be distinguished by a color. So let us consider what are the forces acting within the tension, and what are within the string, and what are the forces which are exerted by the string on the bodies connected to it. So the string exerts a force T in upward direction on the block, right? So let us say the block has some acceleration. Let's say this block has some mass m1 and its acceleration mass ma is given in the question. So let's say the block A has an acceleration in downward direction, or even say let's say it has some velocity in downward direction v. So if block A is moving down, then block B should be moving up with some velocity v dash. Well, we can say this velocity is some, if this velocity is some va, then this velocity can be some vb. What we are aiming to find is that what is the relation between v and vb, and that is the name of the topic, constraint relations. Now we have to find these relations, that how when va moves, then how vb moves. So like you would have identified, we came to the answer, or we came to our objective at the very end of the discussion. So that is what is actually important. First, we have to find the instantaneous power. We learned about the idea of instantaneous power. What is instantaneous power? And then we thought that, okay, what is the net power delivered by the string, and how would the string deliver its power? So we took an example, and then we saw that, okay, we are going to take some points on the pulleys, and then we are going to take power at each point. So that is what we are going to do here also. So let us say this is the point which the tension is going to discuss to deliver some power at. This is the point of contact again. This is one more point of contact, one more point of contact, and this is the point of contact also. So like we said, there are 6 points of contact. So uh, finally, what will come out is that after taking all these points of contact and calculating instantaneous power at all these points, we will be adding the instantaneous power at all these points, and sum of all those power would come out to be 0. So that is the final part which we are looking for. So let us start. So let's say the tension string is some T, and since this is a single string, the tension is going to be T everywhere, and that is the point which we learned, that the tension in the massless string is going to be same everywhere. Tension is acting and is going to act in the direction which we are drawing. Tension T, which it acts along the string, and tension T acts downwards uh, on the roof. So what is the instantaneous power delivered at number 1 point? So the instantaneous power delivered at number 1 point will be T into VA. Now let us take focus on this figure. Tension and velocity, these two vectors are opposite to each other. So the dot product of these two vectors would be negative. So that means that once the tension and velocity are in same direction, their dot product would be considered positive, and once they are exactly opposite to each other, they would be taken with the negative sign. So as per this figure is drawn from mass A. So minus dA plus tension into velocity of the point marked as white. So this point is on the pulley, and this point is in contact with the string, but it is on the pulley, and we are studying the power delivered by string on the bodies. So the pulley is the body, and the pulley, the point of contact on the pulley is not moving. So that means that its velocity is 0. So we can write tension T into 0. Similarly, we would be writing the same thing for this point also. So we would be writing tension T into 0. Similarly, we will be writing this point, this tension T also. So we will be writing T into VB, and same thing here, T into VB. So tension and at the final point T, tension T would be multiplied with 0, and that would become 0. Here I would like to reiterate, at these points the tension and velocity are having same direction, so we have simply multiplied tension with the velocity, and we have done the same process again for this point on this pulley. So this is T to VB, and our idea is that when adding all these instantaneous power, their sum will be 0. So let us calculate further. Upon calculation, we would say that minus TVA plus 2TVB is equal to 0, or VA is equal to 2VB. So this is our constraint relation. Now, how would this help us further? After doing this whole calculation, what we do is that we differentiate this equation. So differentiating this equation, we'll get differentiating with respect to time, we'll get acceleration of A is equal to 2 times acceleration of B. So this is how the acceleration of blocks A and B are found. The relation between these two accelerations are found. For example, Usually when we are solving the question, what we are doing in solving these Pulley-Block questions, we are writing the Newton's second law equation F equal to mn. So we get one equation for this block, second equation for this block. So we have variable number 1, that is acceleration, variable number 2, that is acceleration due to of point B, and we have two equations. But there is one more variable, that is tension, which would again come in both the equations. So we have one and two equations, but we have three variables, so it is unable to solve on its own. So that is where constraint relations comes in the middle, that there is one more equation which is necessary to solve our questions. So that is what is the job of constraint relations is. So after that, usually after arriving at these equations, we draw the force body diagram of block number 1 and the force body diagram of block number 2. We draw the forces and then we solve them, and after solving them, we'll get the value of acceleration of A and acceleration of point B. So in this lecture, let us cover up till this point only. That is the idea. What were the idea of constraint relations? That how to calculate the instantaneous power, and what is the role of instantaneous power in calculating the constraint relation. What points are taken on the pulley, what points are taken on the block, and so on. So and after doing all that, we add up all the instantaneous power to equal to 0 and find the relation. So in this video we'll be covering up to this point only. In the next video we'll be doing some more examples and doing more questions in constraint relations in a bit detail. Thank you.